Hi folks, welcome to another set of ICP video notes. Today we'll be talking about the ideal gas law and how changes in pressure, temperature, volume, or the number of particles will change any other one of those variables. In order to understand the gas laws, we have to make some basic assumptions about how gases work. For instance, we have to assume that in a gas there is a large number of particles that are exactly identical to each other and always in constant random motion. We also need to assume that the distance between those particles is really huge compared to the size of those particles. Also, since those particles are always moving, they don't spend a lot of time being next to each other or next to the wall of the container, so they don't interact with each other. In fact, the particles just collide with each other. They hit each other and bounce off, or they hit the walls of the container and bounce off. We assume that these collisions are perfectly elastic, which means that there's absolutely no energy lost when one of these particles hits another or hits the walls of the container. And lastly, you already know this one, when we're talking about all of the energy of the particles moving, that kinetic energy of the particles, that's thermal energy, and anytime that there's a transfer of that kinetic energy, we call it heat. Here's a few terms that you're going to need to write down and know. They're actually just the variables that we'll use in our equations coming up. The first one is pressure, which we symbolize with a capital letter P. When we're talking about gases, we can define the pressure as the amount of force the gas is applying to the walls of the container. You're probably familiar with measuring pressure in PSI, or pounds per square inch. That's what you measure your tire pressure in. There are a couple other units we could use to measure pressure too, but today we're going to measure pressure in atmospheres, which is abbreviated ATM. Next, we have volume, which is represented by a capital letter V. Volume is the amount of space the gas will take up. I'm sure you're familiar with multiple different units of volume, probably gallons for sure. Today we're going to measure the volume in liters, which is represented by the capital letter L. Next, we have the number of particles, which is shown by the lowercase letter n. This one's pretty self-explanatory. It's the number of particles of the gas. And we measure it in units of moles, which we've talked about before. That's abbreviated as MOL. And 1 mole of a gas has 6.022 times 10 to the 23 particles of that gas in it. Lastly, we have temperature, which is represented by the capital letter T. You're familiar with the 3 ways that we measure temperature, but today we're going to measure in degrees Kelvin, which is represented by the letter K. So let's start off with what I like to call the real OG laws, or the real original gas laws. Robert Boyle found that the pressure is inversely proportional to the volume if you keep the temperature the same. In other words, if you decrease the volume, the pressure will increase, assuming that you're not changing the temperature. You might hearken back to that example of the marshmallows in a vacuum. When you decrease the pressure around those marshmallows, the marshmallows increased in size. Then there's this guy named Jacques Charles who found out that the volume is directly proportional to the temperature if you keep the pressure the same. In other words, if you increase the temperature, you'll increase the volume if you don't change the pressure. A fine example of this is when you take a room temperature balloon, dip it in something really cold like liquid nitrogen, and then it shrinks up in size because the gases inside huddle in together and the volume decreases. And finally, there was a scientist named Joseph Louis Gay-Lussac who found that the pressure is also directly proportional to the temperature if you keep the volume the same. In other words, if the temperature decreases, the pressure will decrease, assuming that you don't change the volume of the gas. We all experience this every winter with the tire pressure in our cars. As the temperatures outside decrease, it gets colder, then the tire pressure also decreases. And then in the springtime, we see as it warms up, the tire pressure warms up, and we've got to let some air out of our tires to decrease the pressure. So after years of working with these 3 gas laws, scientists finally got together and said, wouldn't it be nice if we had this all in one law and we could just do all of our math with one equation? So that's what they did, and here it is. PV equals nRT. You already know PV, N, and T, but there's that pesky capital R in there that you haven't seen yet. They found out that PV equals NT just doesn't quite work very well. They needed a fudge factor, or a constant, a number, to multiply the right side of the equation by, in order to get the correct answer out. So basically, R could be replaced with 0.0821 liter atmosphere per mole Kelvin. It has a really weird unit to it, but as you do the math, you'll see why it's important for canceling out the rest of the units in the equation. So one way to remember the relationship between the variables is to remember the equation and think if the variables are on the same side of the equal sign, they do the opposite thing, or if they're on the opposite side of the equal sign, they do the same thing. For instance, pressure and volume are on the same side of the equation, so if you increase pressure, the volume will decrease. But pressure and temperature are on the opposite side, so if you increase pressure, you'll increase temperature. If that's how you want to remember it and that makes sense to you, then more power to you. I, on the other hand, like to think about the particles and how they're moving inside the gas, and then it just makes a whole lot more sense to me. Really, all these relationships just come down to the amount of collisions that the particles are having. So when we talk about temperature, if we increase the temperature, we're increasing that kinetic energy of the particles, which means the particles are moving faster. If those particles are moving faster, in the same amount of time, they would end up hitting more other particles or the walls of the container more often than they do when they're moving slower. So we're increasing the number of collisions when we increase the temperature. Pressure is the force applied to the outer walls of the container. So if you're colliding more with the walls of the container, you're increasing the pressure. If you were to take the container and decrease the volume, there'd be less room for the particles to move around without hitting each other or the walls of the container, so you'd end up having more collisions that way. And if you were to add more particles into the container without changing anything else, you would have more collisions because you have more particles to collide with each other. So when we look at these relationships, we only ever look at two at a time. We assume that the rest of the variables in the equation aren't going to change. So let's look at some examples that might help us conceptualize this idea a little bit better. So the first question is, imagine yourself, you're at a hotel pool, and you're just hanging out in the pool with your raft, and you decide, even though it's against pool rules, you're going to take your pool raft over to the hot tub. Now you've moved from the pool to the hot tub, increasing the temperature of the raft and the particles inside it, but you're not changing the size of the raft, and you're not changing the amount of particles of gas inside the raft. So to think about this problem, you first have to think, what is it that we're changing? And then you have to think, what variable will change because of that? So we said we're changing the temperature of the gas in the raft because we went from a pool to a hot tub. And it says that the volume doesn't change and the number of particles doesn't change. So you're looking for the change in the pressure. So if we increase the temperature, what happens to pressure if we don't change anything else? Well, think about those particles again. You're increasing the temperature, so the particles are moving more. We're not changing the volume. We're not adding or decreasing particles. So those particles moving more means they're going to hit the walls of the container more. And since pressure is based on how much force is applied to the walls of the container, the more collisions you have, the more pressure you'll have. Let's take a look at the next question. What happens to the volume of a balloon if you increase the amount of air inside of it? And we're not changing the temperature or the pressure. You already know from experience, as you blow up a balloon, the balloon gets bigger. But why is that? When you're adding particles, they want to take up more space and the balloon's stretchy enough. So instead of changing the pressure or the temperature, they're just going to push out more on the sides of the container and give you more room for those particles to move. Here's another question you probably have experience with. When you take one of those plastic water bottles with the lid on it and you twist them, you're effectively decreasing the volume of the water bottle, right? And you're not allowing any of the gas to escape. So since we're not changing the temperature and we're not changing the amount of gas we have, what's going to happen to the pressure inside that container as you decrease the volume? So as we decrease the volume, those same amount of particles are still in there, and there's less room for them to move around, so they end up hitting the walls of the container more. And that increases the pressure. And you probably already know that because there's a high enough pressure that you can just pop the cap right off. So here's another question. What if we were to do that same experiment, but instead we were doing it in a much colder environment? For instance, we dip the bottle in liquid nitrogen. Now we've decreased the volume and decreased the temperature. So now, instead of the pressure increasing, those particles are going to move slower, reducing the number of collisions that we have against the walls, and then our pressure doesn't change.